This is part 3 of the lecture on interaction among independent variables. Now, we look at an example of interaction between two categorical variables, in a logistic regression model. The dependent variable is hypertension, measured as systolic blood pressure being greater than 140. Independent variables selected for this exercise are gender and education. In this analysis, the log odds of being hypertensive is modeled as a linear combination of gender and binary variables for two education categories, not graduated from high school and graduated from high school. Male and college graduate are reference categories. Estimates of parameters of the logistic regression model, without interaction, are shown here. This is a version of the model with interaction. Note that the equation includes two interaction terms, gender times the binary variable for those who have not graduated from high school, and gender times the binary variable for high school graduates. This table is from the output of the analysis. Two numbers in the B column, 0.653 and 0.384, are betas for the interaction terms. The p-value for the interaction terms together is 0.030, shown in the column labeled sig. This indicates that there is statistically significant interaction between gender and education. But it is difficult to understand and interpret the pattern of interaction directly from these numbers. It helps to construct an interaction table. Essentially, it is like the construction of a new categorical variable, combining gender and education. This new variable has 6 categories, such as males who have not graduated from high school, females who have not graduated from high school, males who have graduated from high school, females who have graduated from high school, males who have graduated from college, and females who have graduated from college. The combination of the two reference categories, male college graduates, may be considered the reference category of the new variable. We calculate the value of the sum of terms that include gender-related or education-related binary variables. In this model, we calculate the sum of the values of the 5 terms from -0.506 times x1 to 0.384 times x1 times x3 for each of the 6 groups. For example, let's look at females who have graduated from high school. For that group, x1, gender for females, equals 1, x2, not graduated from high school, equals 0, x3, graduated from high school, equals 1, and x1 times x2 equals 0 but x1 times x3 equals 1. Substituting these values into the 5-term summation, we get their total value of those 5 terms, which is -0.506 plus 0.255 plus 0.384 equals 0.133. In this way, values of the 5-term total are obtained for each of the 6 groups, and those values are displayed in the table at the bottom. Note, the table shows relative differences in log odds of being hypertensive between these 6 groups. But log odds are difficult to interpret. So, by exponentiating these numbers, the 6 groups can be compared in terms of odds of hypertension. The upper table, copied from the preceding slide, shows differences in log odds of hypertension among the 6 groups. The lower table, obtained by exponentiating the numbers in the upper table, shows the ratio of odds of hypertension for each group to the odds for male college graduates, which is the reference group. For example, the lower table shows 1.290 in the row labeled HS, and the column labeled M. This means, the odds of hypertension for male high school graduates is estimated to be 29% higher than the odds of male college graduates. The odds of hypertension for females who have not graduated from high school is estimated to be 92% higher than the odds of male college graduates. For both males and females, the odds ratio decreases from the top to the bottom in the table, indicating lower education is associated with higher risk of hypertension. But the educational differences are greater for females than for males. Let's compare the two numbers in the top row and the bottom row. They are 1.654 and 1.000 for males. This means, for males, odds of hypertension for those who have not graduated from high school is 65% higher than that for college graduates. But the corresponding numbers for females are 1.916 and 0.603. This means, among females, odds of hypertension for those who have not graduated from high school is 3 times as high as that for college graduates. How many interaction terms are needed for examining interaction of two categorical variables? In the example we just looked at, just 2 terms, x1 times x2, and x1 times x3, were used. but shouldn't we use 6 interaction terms because the combination of gender and education produces 6 groups? The answer is, if the numbers of categories for the two variables are m and n, the number of interaction terms needed is m-1 times n-1, not m times n. In the case of gender and education, gender has 2 categories, and education has 3 categories, so 2-1 times 3-1 equals 2 is the number of necessary interaction terms. Put in another way, first, for each categorical variable, all categories that are not the reference category are selected. For gender, male is selected because female is the reference category. For education, not graduated from high school and graduated from high school but not from college are selected because graduated from college is the reference category. Then, all possible combinations of the selected categories are made. In this case, females who have not graduated from high school and females who have graduated from high school are adopted as interaction terms in the regression model. This table shows the 2 adopted combinations in a matrix form. The third example shows an interaction between 2 numerical variables. This linear regression model tries to predict systolic blood pressure from age and diastolic blood pressure. An interaction between age and diastolic blood pressure, in the form of product of these 2 numerical variables, is not included in the first equation, but included in the second equation. I put the third and fourth terms of the second equation together in parentheses, in order to look at age dependency of relation between diastolic blood pressure and systolic blood pressure. X2 is diastolic blood pressure, and the terms inside the parentheses, 0.366 plus 0.002 times X1, represents the relation between diastolic blood pressure and systolic blood pressure, which seems to be stronger at older ages. If we select ages 20 and 80, and substitute 20 and 80 for X1 in this equation, we get these 2 equations at the bottom, one for those at age 20 and the other for those at age 80. The coefficient for diastolic blood pressure is a little larger for age 80 than for age 20, which seems to suggest that diastolic blood pressure and systolic blood pressure may be more closely related with each other at older ages. I want to make a few remarks on interaction. First, for any combination of 2 independent variables, you can check if there is a noticeable interaction between them, in relation to your dependent variable. But if you have 6 independent variables, it is quite tedious to check all 15 two-factor combinations. If you have 20 independent variables, the exhaustive checking of all combinations would require your computer to do a huge amount of computation. Therefore, you should think about the independent variables that you have selected, think which combinations of those independent variables are likely to have significant interaction effects on the dependent variable, and include those combinations as interaction terms in the model. In other words, among all possible interaction terms, you should select only those that you think are plausible. If possible, use programming software to check all the two-factor combinations of your independent variables and select the pairs that show significant effects. Secondly, if a categorical variable is expected to interact with many other independent variables, do regression for each of the categories, that is, stratify the analysis by that variable. For example, if you select age, education, and race as independent variables, and think that each of them are likely to interact with gender, you should do a regression on age, education, race, etc. separately for males and females, that is, you should do 2 regression analyses, one for females and the other for males instead of one regression analysis including all gender-involved interaction terms in your regression model. Third, although we have been studying about two-factor interactions so far, we can think of three-factor or higher-order interactions, such as a gender-race-education interaction. For example, a product of 3 variables, x2 times x3 times x4, can be included in the model as a three-factor interaction term. But, three-factor or higher-order interactions are rarely used. Fourth, it is very important to clearly distinguish between interaction and association or correlation. The minimum number of variables that are associated or correlated with each other is 2. Variables x1 and x2 are strongly associated if variations in x1 and variations in x2 are closely related to each other. But a two-factor interaction involves 3 variables. It is an interaction between x1 and x2, in relation to y. If there is an interaction between x1 and x2 in relation to y, the association between x1 and y depends on x2, and similarly, the association between x2 and y depends on x1. It is possible that there is a strong interaction between x1 and x2, in relation to y, even if x1 and x2 are not associated with each other at all. So, it is important not to confuse interaction with association. Finally, significant interactions in statistical data are not very common. The additivity in basic models of regression may seem a strong assumption and an oversimplification, and we may feel, the real world should be full of interactions. But in much more than 50% of the times when we introduce interaction terms into our models, they turn out to not be statistically or substantively significant.